Good day, everyone. Good day, viewers. I am Gamba, a Doctor of Philosophy in Mathematics Education student of Sorsogon State College, Sorsogon City, Philippines. The aim of this video is to demonstrate the process of Gauss-Jordan elimination. So, at the end of this session, you would be able to first understand the process of Gauss-Jordan elimination and second, solve a system of linear equations using Gauss-Jordan elimination. So, what is Gauss-Jordan elimination? Gauss-Jordan elimination is a method of solving a linear systems of equations. This is done by transforming the system's augmented matrix into reduced row echelon form by means of row operations. It was introduced to us by geodesist William Jordan way back in 1842 to 1899. Okay, right now, I am going to show you the Gauss-Jordan elimination method, or the process of Gauss-Jordan elimination method. Here's now the steps. First, write the augmented matrix of the system. Okay, how to do this first step? So, for instance, let us solve the following system by using the Gauss-Jordan elimination method. For instance, you have this systems of linear equations, x plus y plus z equals 5, 2x plus 3y plus z equals plus 5z equals 8, and 4x plus 5z equals 2. Alright, let us write the augmented matrix of these systems of linear equation. By doing so, we just write the numerical coefficients of each equations. Okay, so for the first equation, x plus y plus z equals 5, it is written as 1, 1, 1, then 5. For the second equation, 2x plus 3y plus 5 equals 8. It is written as 2, 3, 5, and 8. And then for the third equation, you noticed here that there is no variable for y. So we just simply put it in 0. So it can be written as 4, 0, 5, and 2. This is now the augmented matrix of the given systems of linear equations. The second step now is use row operations to transform the augmented matrix in the so-called reduced row echelon form. This is an example of a matrix in reduced row echelon form. To be in this form, a matrix must have the following properties. First, if a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. We call this the leading 1. If there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. In any two successive rows that do not consist entirely of zeros, the leading one in the lower row occurs farther to the right than the leading one in the higher row. Each column that contains a leading one has zeros everywhere else. So I'll just explain to you what do we mean by this reduced row echelon form. On the first row, it signifies that we have obtained the value of the first variable, which is in this example 4. And the second row, it means that we have get the value of the second variable, which is 3. While in the third row, we have obtained the value of the third variable, which is negative 1 in this example. Going back to our example, let us transform this augmented matrix into reduced row echelon form by using row operation. You can choose any rows here in order to reduce this into reduced row echelon form. So in this example, I will start in row 2 and subtract it to twice the row 1. So in this case, it is now equal to, so since the first row is not involved, we just write it like this and perform this one. So R2 minus 2R1, so 2 minus 2R1 is equal to 0. For the second, we have 3 minus 2R1, we have 1. And then 5 minus 2 R1 equals 3. Then 8 minus 2 R1, which is 8 minus 2 times 5, which is 10. 2 minus 8 equals negative 2. And then we just write this since it is not being affected for 0, 5, and 2. The next, we can perform R3 minus 4 R1. So in this case, we perform this using this row operation, R3 minus 4 3 R1. So this is equal now to, so again, this first row is not involved, so we just write it 1 1 1 5, and then the second row is not already also affected, so we just write it 0 1 3 and negative 2, and then let's perform this row operation R3 minus 4 R1, which is, for the first one, 4 minus 4 times the R1, which is 1, is equals to 0. And then 0 minus 4 R1 is negative 4, and 5 minus 4 R1 is 1. And then 2 minus 4 R1 is negative 18. Okay. Okay, let's continue. So this time, I'm going to reduce this negative 4 here by using this row operation, R3 plus 4 R2. Then we get, so again, this is not affected. We just write it like this. Then 0 1 3 negative 2. Then let us reduce this. R3 plus 4 R2 is again 0. Negative 4 plus 4 R2 is 0. And 1 plus 4 R2 is 13. Then for the last is R3 plus 4 R2, negative 18 plus negative 8 is negative 26. Then let us reduce this to make this 1, and then we can use 113 R3. So we have now, so the reduced form now would be 115 0 1 3 negative 2, and then 0 0 1 negative 2. So we just divide this 13 by 13. R3 is 13 divided by 13 is 1, and R3 is negative 26 divided by 13 is negative 2. Next is, let us reduce this from this one. Let us reduce this to 0. So we can use the row operation as R2 minus 3 R3. So the reduced echelon form now is, so this is not affected. We just write it this way again. 1 1 1 5 and 0 1. So this becomes 0 because R2 is 3 minus 3 R3. Our R3 is 1. 3 times 1 is 3. 3 minus 3 is 0. Well, for this one, negative 2 minus 3 times negative is positive 6. So negative 2 plus 6 is 4. And then we just rewrite it this way, 0, 0, 1, negative 2. So as you can see now, what we need to reduce is this 2 here. So what are we going to do is to use this row operation, R1 minus R3. So in this case, we have since this 2 here is not affected, we just rewrite this as 0, 1, 0, 4, and then 0, 0, 1, negative 2. Then the other one is, so R1 is 1 minus R3 is again 1, and then 1 minus 0 is 1, then 1 minus 1, 1 minus 1, since our row operation is R1 minus R3, so 1 minus 1 is 0, and 5 minus negative 2, 5 minus negative 2 equals 7. So the last number that we are going to reduce in this matrix is this 1, to have a reduced row echelon form. Okay, so what are we going to use? A row operation is simply R1 minus R2. So in this case, it is now being reduced into, so since these 2 rows here are not affected, so we just write it 0, 1, 0, 4, and then 0, 0, 1, negative 2. So for this one, we use this row operation R1 minus R2. So 1 minus 0 is 1. 1 minus 1 is 0. And 0 minus 0 minus 0 is 0. And 7 minus 4 is 3. Therefore, from this final matrix, we can now read the solution of the system, which is x equals 3, y equals 4, and z equals negative 2. So going back to our given equation, systems of linear equations, we have, using the Gauss-Jordan elimination method, we have find the value of the variables x, y, and z as x equals 3, y equals 4, and z equals negative 2. So that could be all. Thank you.